In this video, I will talk about exponential functions and their graphs. Specific objectives of this lesson are recognize and evaluate exponential functions with base A, graph exponential functions and use the one-to-one property, recognize, evaluate, and graph exponential functions with base E, use exponential functions to model and solve real-world problems. We're going to go ahead and get started with defining what an exponential function is. So far, this text has dealt with mainly with algebraic functions, which include polynomial functions and rational functions. But in this chapter, you will study two types of non-algebraic functions, which are exponentials and logarithms. And logarithms is what we're going to do next. But in this lesson, we're going to focus on exponential functions. And these are functions that we call transcendental functions. So the specific definition is f of x equals a raised by x, where a is a positive number, the base. This is what we call the base. And a is not 1, and x is any real number. So you guys realize this base a is generally a fixed number. So this number is generally fixed. And x is a real number, and x in this case is generally the variable of interest. Okay, so base is going to be a constant number, and then exponent is the variable. So what that means is that variable x is your input. So your input is the exponent, right? Your input is this exponent. Exponent is the input. And then the whole thing, when evaluated, whole thing, a to the x, whatever that value is, this whole thing is the output or the y value for this function. Okay? And then the base a equals 1 is excluded because it yields f of x equals 1 to the x. And you guys realize 1 raised by anything is always 1. So that is a constant function and not an exponential function. Previously in algebra classes, you may have learned about how to evaluate exponentials, which is very similar here. So we can do examples like 4 raised by 3. What this means is that you multiply 4 by itself 3 times, and then you get 64. And then 4 to the 1/2 is 2, because you're taking the square root of 4. So what this represents is that 4 to the 1/2, which is the same thing as square root of 4, which is 2. However, to evaluate 4 to the x for any real number x, you need to interpret forms with irrational exponents. So you're going to get situations where you're going to have irrational exponents. Because again, x or the exponent could be any real number. Input could be any real number. For the purpose of this, I'm just going to provide you guys what I mean by that. So you guys realize the exponent is an irrational. It's square root of 2. And then it actually works because like you can actually compute for based on whatever a value we have, you can compute a to the square root of 2. All right, so here's an example. You're going to use calculator to evaluate each function at the indicated value of x. So for part A, you're given f of x equals 2 to the x, and evaluate that for the value negative 3.1. Second one, 2 to the negative x, evaluate that for x equals pi. So you guys realize pi is a specific number that is approximately equal to 3.14. But because your calculators are highly likely having pi as an input, you can just use pi symbol to evaluate it. And then lastly, evaluate 0.6 raised by x, and then put x as 3/2. So I want you to pause the video for a second and then evaluate this for yourself before moving on to the next chapter. I recommend using either an online calculator or whatever calculator that you have at home. So please pause the video, try this for yourself, and then practice. All right, hopefully you had a chance to practice. Now I provide the solution for these problems. So for part A, you're going to replace x with negative 3.1. And then on a graphing calculator, you will probably do 2, use this tilde symbol, and then put negative 3.1 and hit enter. And then you should probably have 0.1166291 on the display. Similarly, for all the other functions, you should get these values. All right, next thing we're gonna do is we're interested in graphs of exponential functions. So we're gonna examine graphs of exponential functions. So here in this example, I'm gonna take a look at two graphs, f of x equals 2 to the x and g of x equals 4 to the x. So here I provide a table of values for x, and then I'm gonna evaluate each of these functions for the given x's. So when x is negative 3, 2 to the x becomes 1 over 8. So you may be wondering, how did that happen? So think of it this way. So 2 to the negative 3, that's what we're evaluating. And because negative exists, you're gonna flip the number. So it's gonna become 1 over 2 to the third, because what negative at the exponent does is it flips the number, and you can write it as a fraction like I did here, and 1 to the 2 to the third is 1 over 8. So that's why we're getting 1 over 8. And you know, if you use your calculator, you're gonna get the same value. So for this guy, so 4 to the negative 3, so we're gonna do similar work. We're gonna flip that number as 1 over 4 raised by 3, and then you get 1 over 64. So you evaluate x's and then find values here on the second and the third rows on the table. And then if you actually graph using a graphing calculator, or I mean, you can basically just plot these values that you just found. And then if you like connect these numbers, these values, you're gonna realize the function is gonna look like, one is gonna look like that, and then the other one is gonna look like this blue line, which is for 4 to the x. So you guys realize both graphs are increasing. Moreover, the graph of 4 to the x is increasing more rapidly than 2 to the x. So now I'm gonna talk about the general characteristics of exponential functions. Okay, so generally speaking, when you're given y equals a to the x, where a is positive, the base is positive, the graph is more or less is gonna look like this. It's always gonna look like kind of lower on the left and then increasing on the right. It's always gonna look like this. This shape is when you have a to the x. It's always gonna look like that. So your domain, meaning possible inputs, is always gonna be negative infinity, positive infinity. Range is always gonna be 0 to infinity. You guys realize you're never gonna get a negative y value because the function or the curve is always above the x-axis, so it's always positive. Y-intercept is generally 0, 1, because you realize that when you have y equals a to the x, when you replace x with 0 here, you're gonna get a to the 0, which always gonna be 1. No matter what a is, it's always gonna be 1 because the exponent is 0. And then it's always increasing. X-axis is a horizontal asymptote, so you guys realize the function is never gonna touch the y-axis. And then this function is always continuous, meaning there's no hole, there's no break, there's no inconsistencies. So yeah, that's the general characteristics of exponential functions. Now I'm gonna do a similar work with a negative exponent version of this. So whenever there's a negative for the exponent, the function changes a little bit. So here the domain is the same. Any x should work. Range is the same, it's always positive. So y values are always positive. Y-intercept is the same, but the only difference you guys realize it's the function is decreasing because it's bigger on the left and it's smaller on the right. So it seems to be decreasing. And then x-axis is still the x-axis is still the horizontal asymptote, and the function is still continuous. So the only difference is you guys realize this function is decreasing. And then I'm gonna explain why this is the case. Here with the previous one, you guys realize the shape looked like that. So I'm gonna try to bring that here. Okay, so you guys realize this guy is y equals a to the x. You guys see the difference here is that they're almost identical, but they're reflected above the y-axis. So the reason why it looks like that is because you guys realize this one has the negative version of x, so the input is multiplied by negative. So, and because the input is multiplied by negative, you guys actually see that this is a reflection by the y-axis. Reflection by the y-axis. That's all that is. So when you multiply the input by negative, it reflects the curve by the y-axis, which is something we learned with the topic of transformations. It's the exact same idea. All right, so next thing we're gonna understand here is that we realize that the graphs of exponentials are always increasing or always decreasing. As a result, these graphs should pass the horizontal line test, which is something we previously learned. If we can go back to these graphs and test that a little bit, you guys realize horizontal line test says if you draw random horizontal lines, if the line crosses the function at 2 points, then it's not one-to-one. But in this case, it always just intersects just exactly once, so we don't have any issue. So for that reason, this exponential functions passes the horizontal line test, meaning they're always one-to-one. They're always one-to-one. And then one-to-one is very useful for algebraic stuff. We're not gonna do too much of that, but I'll probably do a little bit of it. But if you have problems like, you know, a positive or a is not 1, then you have a to the x equals a to the y, if and only if x equals y. So if you have two exponentials that are equal, then their exponents must be the same thing. So this is due to the one-to-one property. All right, next thing we're gonna learn is the natural base e. So in many applications in mathematics and other quantitative sciences, the most convenient choice for the base a is the irrational number e approximately 2.718281828. So this number is a special number and we call it natural base. It's a specific number. Then the function f of x equals e to the x is called natural exponential function. So e to the x is a natural exponential function. It's gonna, of course, look like this graph on the right. It's gonna look like an exponential function. The only difference is, again, base is e. One thing you guys need to realize is that f of x equals e to the x. So you guys realize e, the base, is always a constant number, right? Base is a constant number, which is given right here. And then x is gonna be my input. Here's an example to evaluate natural exponential functions. So use your calculator to evaluate the function f of x equals e to the x at each value of x. So x given -2, x given -1, 0.25, -0.3. So please stop the video and then practice by yourself and then take a look at the solution on the next slide. All right, here are the solutions. So you're gonna enter -2 for x, and then when you do that, you get 0.35. And then answers for each of these, you should get similar results. All right, last thing I'm going to talk about in this video is going to be some of the applications of exponential functions. Specifically, one of the most familiar examples of exponential functions or exponential growth is an investment earning continuously compounded interest. So you guys may have seen this formula before, where when banks or like financial institutions compute compounded interest, they use a formula like this: A equals P times 1 plus R over N raised by N times T. This seems to be a very complicated thing, but it's actually not. So what A is A gives you the balance. So A is the balance. P is the principal. So it's basically your down payment. And then R is interest rate. So R is just the rate. And N is the number of compoundings per year. So number of compoundings. So when we say compoundings, is what we mean is how many times the rate is being applied. So if the compounding is every month, then in each year you're gonna apply it 12 times because each year has 12 months. And then last thing is T. T is the time. And then that's generally in years. So you guys realize this whole thing actually similar, because it's an exponent. So it's actually similar to something like y equals a to the x. And I'm going to tell you why it's an exponential function, why it's similar to an exponential function. It's because all these p and r and n, these are all constant numbers. Okay, so p, r, n are constant numbers. So these are not variables. These are constant numbers. However, the only variable in this scenario is the t. So t is time, and that is our variable. So because of that, and because the variable is in the exponent, you guys realize here's my variable t. Because for that reason, it looks like a to the x, because variable is in the exponent. So that's how you know this formula is actually an exponential growth. That's how you know it. So here I put the compound interest formula more generally as a definition from the book. So if you have n many compoundings per year, you're gonna look like this formula. And then if you have continuous compounding, which is something I would generally discuss, but I'm not gonna get into detail. This is actually when you have almost infinitely many compounders. Like every time the rate is just like continuously being applied. It's not just like per month, it's not just per day, it's just every time it's being applied. So those situations is when we use E for the bottom or the base, and then the exponent becomes R, the rate, times the T. So that's just the formula is going to look different when we have continuous compounding. So what I mean by compounding is how many times the rate is being applied. So I'm going to take a look at an example and explain how we can use it. So you invest $12,000 at an annual rate 3%. Find the balance after 5 years when the interest is compounding quarterly, monthly, and continuously. So we're going to compute what the balance is going to look like after 5 years for each of these scenarios. So first, we're going to compute for quarterly compounding. Okay, so what quarterly means is every year has 4 quarters. So what that means is n is going to be 4, because you're going to do 4 times a year. That's why we use n equals 4. And then 5 is given is my time. So I'm going to say t must be 5. And then rate is 0.3. We always convert this into a decimal. So 0.03. And then what we do is we replace all these things into the formula. So you guys realize P is the principal. P is the down payment, in other words. So $12,000. 1 plus R is 0.03, N is 4. You replace all that, and then N times T, N is 4, and then T is 5. And then when you compute this whole thing using your calculator, you're going to end up having 13,934.21. So that's going to be your balance at the end of 5 years. Okay? So that's your balance, total balance. And you guys realize your principal was $12,000. What happened is that your money grew because you earned money based off of interest. So next scenario is we're going to do similar work but for monthly compounding. So you guys realize because it's monthly and because 1 year has 12 months, N has to be 12. So it's going to be compounded every month, so N has to be 12. So do very similar work except N must be 12. And then compute that, you're going to get 13,939.40. That's going to be the balance after 5 years. Lastly, we're going to do continuous compounding, meaning it's always going to be compounded. It's always. As long as the money is in the back, it's always being compounded. So in that scenario, you use another formula, a different formula. A equals P E raised by R to R times T. So principal is the same thing. R is our rate, T is our time. So all you need to do is to compute that exponential number, 12,000 E raised by 0.03 times 5. When you do that, you're going to end up having 13,942. That's going to be your balance. So you guys realize that this was for continuous. The previous one was something like 939.4. And then the previous one was something like 34.21. So you guys realize this was quarterly. This is your balance for monthly. And then that last one is for continuously. So you guys realize you get most out of your money when you do continuously compounding interest. But when you do monthly interest, you're getting this much money. If you do quarterly interest, which is less of all the others, which is going to be a less amount. It's not going to make too different for your investment, but depending on how much you're investing, it might make a difference. All right, so that's going to be all for this video, and I hope you guys enjoyed learning about exponentials.